A little background on myself. I was educated at Duke University. At 20-some years ago, you had certain characters there, like Berger was there, Don Berry was there, and Mike Levine. So it's a Bayesian place. We were, of course, the token frequentists there, but we sort of got that, we were part of that culture, and so it was quite a bit of my background. This talk here came up, this was a question I was given about 5 years ago. A physician asked me a question. I've been working on pharmaceuticals for about 20 years. And he wanted to know if we just did a study, which they did. They had 20 subjects in it. The question was, they had one success. The question was, we had one success out of 20. What would be the probability if we redid that trial with 100 subjects that would have 5 or more successes? Well, I thought about it a little, and I thought, well, that sounds like that might be a Bayesian type question. Of course, there's other simple ones to it. So what this talk is designed to do, basically the audience at the time was a lot of physicians, statistical biostatisticians, and the background was varied. So my assumption was that no one had any Bayesian knowledge. And I think it's sort of fortunate that I'm going first, because this is sort of a, why would you use this, how does it work, that type of thing. I'm going to, in the talk, when you get to page 25, I'm going to cut it off. It actually goes a little further, but that'll be enough. I'm going to give 2 Bayesian examples, very simple. And then I'll come back, then I'll come back to the question. So let's get started. Okay, there's the problem. Go on to the next slide. The assumption is the basic understanding of probability. A few results of interval calculus. If you don't know interval calculus, just think of sums. But each will be explained at the appropriate time. So basically, I assume that you have that you're mathematically inclined. So the real assumption is a willingness to. Okay, I've already said that. Let's move on to the next one. This is Bayes' theorem. This is the discrete case, and basically what it says. This is out of any undergrad textbook. Suppose we know the probability of it. In other words, suppose we know the probability of this, we know the probability of that, we know the probability of this right here. Then we have some conditional. We know what the probability of B given A is, B given A2, and B given A3. The question might be, well, if we have B, what's the probability of A1, for example? That's Bayes' theorem. So let's see how we would actually go through and do that. So from Bayes' theorem, or from just conditional probability, we know that the probability of A and B is the A1 is the probability of A1 times the probability of B given A1. But also we have that this is equal to the probability of B times A1 given B, and that's what we want. We want the probability of A given B. So at this point, it's just a little algebra. We get the probability of A1 given B is the probability of A1 and B times the probability of B. We already know the numerator. We stated that. So what's the denominator? And that's simply all the ways that we can get B. We get B with A1, A2, A3. And so what we're looking for, that's equal to B's probability of A1. B given A1, and we're assuming we know all of these. A2, B given A2, so forth and so on. So in the end, the probability of A1 given B is equal to probability of A1 times the probability of B given A1, all divided by B of B. And to match what you'll see in the textbook, that's the final result there. This is referred to as now we refer to this as the posterior probability of AK, whereas the predated distribution is referred to as the prior distribution. So, I'm going to use, as everyone else does, pi of A will be used to denote the prior, and in this case I'm going to use f of A as the posterior. At any time, if you have any questions or stop me, I'm happy to address those, and keep in mind when we get to 25, I'm done, so I think we have plenty of time. Okay, this is the first example. And this would make sense to physicians. We have a disease X, it's prevalent in 1 person out of 10,000. There's a test for detection of disease X. If you have the disease, this test will be positive 99% of the time. If not, if you don't have the disease, you'll still test positive 1% of the time. That's a false positive, that's called a false positive rate of 1%. Now the question is, what is the probability that a person who tests positive for disease X actually has disease X? Well, this is Bayes' problem. So let's get used to the notation. We have pi of x, the posterior, and an x. Any knowledge is, I'm not going to try to say that, it's that. And of not having it, of course, is 1 minus that, this number here. Now, the probability of being positive given x, that was the first statement, is 0.99, and the probability of being positive given not x is 0.01. Okay, the probability of, now what we want, the question we have is what is the probability of having disease X given that you have a positive result? Well, that's this right here. It's the probability of Xn being positive divided by the probability of X. Well, the probability of Xn positive is equal to the probability of X, which we know. And it's also times the probability of positive given x, which also gives you that. And the probability of being positive, how are we positive? We're either positive with the disease or we're positive without the disease. So that's going to be the probability of having the disease times the probability of positive if you have the disease, plus the probability not times the probability of positive given that you're not. Well, if we do some, this is the interesting thing. I'm not going to say all this stuff. If you are positive, the posterior probability of x, given that you're positive, is less than 1%. And that's a well, I mean, that happens in medicine a lot. If you test positive or something, doesn't necessarily mean you have it. Questions?
I'm just curious, could you state Bayes' rule using the terms like false positive or whatever? Because it's kind of, for me, it's a little hard to follow.
Okay.
You know what I mean?
Let's see if I can put it together. If I have it right, I could. Basically, Bayes' rule, if you have false, you want the probability of x given, no, you want the probability of having x given that you have a positive result.
Right.
So that's going to be the probability of x. It's going to be the probability of having x and a positive result divided by the probability of having a positive result. The probability of having a positive result. How do you have a positive result? We either have x with it, so it's x and positive, plus the probability of having positive without x. So that's your numerator, that's your denominator. What goes on here is that if the disease in this case is so rare that if you were tested positive, it's more likely that you came from the larger population. If I go back, I'll try to.
This one.
Oh, am I going the wrong way? Let's go. Let's look at this. Forget this part here, okay? Suppose that this here is very small, okay? But B takes up most of it. Now also suppose that this is very large. This is 1,000 times larger than that. But B takes up a very small portion. But when you look at B here, remember it's big, think of this as 1,000 times bigger, you're more likely to be here than you are over there if you've been tested positive. And that's what's going on. If I had a piece of paper, I could draw that. But that's what's going on.
So,
Yes.
if I get it right, what you're saying is, okay, the odds for the population as a whole are 1 out of 10,000.
Yeah.
So out of those 10,000, 9,999 don't have it. The odds that you'll get false positives out of it are 1%.
Right.
So,
But that's 1% of,
that's
say,
1%,
millions of people, yes.
9,999. So
Yeah.
if you get a hit, you could very well be one of those false positives
It's one of,
in that 9,000.
in fact, there are more false positives out there than there are.
Amazing. I've never
Yes.
understood Bayesian
Yes.
before.
There's, yeah, that's the whole point that's going on. I don't know where it came from. It's just I have one. So now I got to figure out where did it come from.
Can I ask a question? I didn't quite understand the summary of the result. If you
Oh, I went through it too quick. That's my fault.
if there are one in 100,000 people that have this disease, and the test is 99% accurate, what is your chance of having the disease if you test positive?
1%.
1%?
In this example. Yeah. I'm not going to look at it. Here's what's going on. If you have the disease, you have a test that says this test will say positive 99% of the time. Okay? 99. If you have it 99% of the time, you're going to have the disease. So if there's 100 people, only 100 people. Let's forget this. There's 100 people that have the disease. 99 of those are going to be test positive. Now, we got 4 million people that don't have the disease. 1% of those will test positive. What's 1% of 4 million? Is it 40,000?
40,000.
So here you got 99 have the disease, 40,000 have the disease. All I know is he has the disease. Where is he likely to come from? He's likely to be one of those 40,000. Okay, here's another one. When I read through this, I thought I had different planets on here, but I must have changed it for that. So what we have is we have 3 population. In one population, we have 40% redheads. Another population, we have 10% redheads. The third one, we have 5% redheads. A random sample from one population, or truth in this case. What's the truth? We don't know what the truth is. A random sample from one of these truths is selected. Of 8 selected, 1 is a redhead. Now, draw a larger sample from the same population. You can see how I'm setting this up for the real question. Now draw a larger sample from the same population. What is the probability of, if 50 are selected, you get 6 or more redheads? I've complicated this a little bit because I'm trying to move toward that question that I originally had. So first I'm showing you how Bayes work. Now I'm just sort of twisting it a little bit. This is exactly the same type of question. Okay, we just need a bit more information. We need to know the prior probability of each population, or truth. Perhaps we have some knowledge of this, perhaps we don't. If not, we can always use what's called an uninformed remark. I don't know what the probability of being on this planet or that planet or this population or that. So I'm just going to assume they're all equally likely. And that's what we're saying here. The probability of each pop is 1/3, i.e. 1, 2, and 3. Now, probability of at least 6 out of 50. Well, how do I get 6 out of 50? That's going to be a binomial problem. Well, actually, there are 3 disjoint things going on here. I'm either in a population that has 40% redheads, in which case I want the probability of being there on 40% times this binomial probability, that is 6 of 50, or at least 6 of 50, given the 40%, and so on. These are all disjoint events, right? I'm on one of the population, I can't be on both. So this adds. So it's a probability of the others. I'm not going to say them all, but everyone agrees, right? These are the ways that it can be done. But we already have seen data. That's the point. We've already seen data. So what is that percent? The probability of the population will be a posterior and not a prior. Remember, the prior was 1/3. So first we have to obtain the posteriors. We've seen data.
So can I practical question?
Sorry.
Can I ask that question?
Well, of course you can.
So 3 populations, but actually there's only 1 truth, is that?
That's right.
Okay, I'm trying.
Well, now you're getting into I don't know if this still exists out there, but the buzz between the classical statisticians and the Bayesians, I tend to be a closet Bayesian, so I feel if you don't know something, assign probability to it. You've seen the thing that box is either in the box or it's not in the box. I think there are probabilities. So, even though I was trained classically, I
Draw from the population.
that's true. And when you have the box either contains the rabbit or it doesn't, and that's yeah. In this case, I'm willing to assign probability. I don't know what the truth is, but I have some insight because I saw some data. I saw, what was it, 1 out of 8? Is that what I saw? Okay, yeah, I saw 1 out of 8. Now, what I need to do is come up with the post-area probabilities. The probability of 40%, 10%, and 5% of each a third. I assumed them uninformed prior. The probability of 8 given 40%, that's both conditions, is equal to binomial 1 of 8 on 40, right? And probability of 10%, 1 of 8 on 10, and the probability of getting 1 of 8 given 5% is a binomial with p of 5%. Do I need to slow down, or am I going too fast? Do you have time to absorb that? Sometimes you just need a few minutes to absorb. I used to sit in classes and algebra, I was getting lost and I figured out later. Okay, where of course B denotes the binomial distribution. Did I
What's
do
the
it?
probability of
I'm sorry? Yeah.
Probabilities to
100%, because I used the posterior. I did
It's
it.
a posterior.
I did it, yes.
Okay.
Okay, this is just how binomial probabilities work. Is everyone familiar with this, or should I go through it? This is just how a binomial probability works. Combination, S successes on N trials given probability is a combination of S on N. A probability of S successes times the probability of N minus S failure, so forth and so on, where Q is equal to the probability. I don't know. I have as much problem with algebra as everyone else. But I want to convey the big picture. We can see this geometrically, we own it. Okay, now, the probability of 40% and 1 out of 8. The probability of 10% and 1 out of 8. The probability of 5% and 1 out of 8. That's all the ways I can have 1 out of 8. So that's given by, I've already set this up. It's the prior times the binomial probabilities. There's my combination 1 on 8, 0.4, point so forth and so on. And when all said and done, the probability of seeing 1 out of 8 is what you have right there, given the conditions I set out.
So that, for example, in the first line, the last part, the 0.6 raised to 7th power, that comes out of our binomial expression.
Yeah.
Calculated.
Yeah. Basically, we're one-third's a chance that we're in that population that has 5% success rate, or successes being a red hat. We saw 1 of 8, so these things get, if you list them out, they get commuted around, but there's 8 different ways it can happen, given the first, second, third. And this is the probabilities of each given sequence of that. There we go. And that's what that's.
Okay, so the 7 comes from 8 minus 1.
Yes, yes. Okay. I have 8 subjects. 1 of them was a red hat. 7 of them were not. So I can take one sequence. What if the first one is a red hat? That carries along a probability of 5%. What about the next one? 95, 95, 95, 95. And there's 8 ways that could happen, because now the second one could have been a red hat. So now it's 95, 95, so forth and so on. It's all the same. Again, it's all the same. The bottom line is that's the probability given of 5% and 1 out of 8. Now this isn't the probability of 1 out of 8 given 5%. is the probability. Actually, that would be 3 times that amount because I multiplied it by 30. All right, so when we actually keep in mind that this is my probability of 1 out of 8, this is my denominator, each of these are my numerators. Because each of these, this here is that big oval that I saw that I showed you in the beginning. Each of these is how the ovals cut out. So the probability of 40% is just this divided by that. 10% is the 3/8 divided by that again. And this is your posterior probabilities. So that's what I'm going to work with when I answer the question. I had data. If I didn't have any data, but I had data, so this to me will give me a better answer. Questions? Yes.
What's the effect of the 1/3 assumption of the priors? I mean, there's not really much information in there.
That's it. What you got? What? I can't do any better than that without bringing in.
But how does that affect the binomial equation? To what extent does that contribute to the final answer?
It doesn't contribute to the binomial equation at all. What it affects is how you weight each of these occurrences here. Maybe I have reason to believe that this never occurs, that never occurs. In which case, the answer would be 3 times that. Okay, now let's see. Okay. Okay,
But what you're saying is if we've got a Schrodinger's cat situation,
Yeah, okay.
then the best we can do until we get more information later on.
Cat's half alive and half dead.
alive, half dead.
Whatever that is. I think Schrodinger, when he did that, he was sort of showing how absurd some of this stuff could be. That was his motivation. Did I already do this one? Probably. This is, now we're back to the question. The probability of at least 6 of 50 given 1 of 8. Well, how does this happen? I get 6 of 50 with the 40% population, plus I get 6 of 50 with the 10%, plus I get 6 of 50 with the 5%. These are all disjoint. 2 truths can't be true at the same time, and one of the truths have to be true. That was my statement. So basically, the probability of seeing 6 of 50 redheads on the planet where there 40% were redheads is this right here. And of being on the planet. The probability of being in the population that had 10% redhead and seeing the 6 of 8 is given by that number and so forth on. So the final result is the probability of seeing 6 or more. Was it exactly 6 or more redheads is, I think, was it exactly 6? Is 32.8%. Questions? Given all the information that I. Of seeing 6 or more, because I've said that this here is the reverse cumulative distribution. So that's, yes.
Your question is, if I have observed 1 out of 8, then I want to predict the probability of seeing 6 out of 50?
6 or more of 50. Yes.
That's giving.
Yeah, I've seen 1 out of 8. I saw 8 people walk by. One of them was a redhead. Oh boy, I want to go out and gather 50 people. What's the probability that I get 6 or more redheads in that group? I don't know what population I'm in. Yes.
Oh, okay. You don't know what population you're in.
I don't know what population. I have no idea.
That's why you have to give equal weight, because you don't know when you
I have
made that
no idea.
observation.
And that's called non-informed prior.
Then those F 40% should be F conditional, 40% given when. Okay, is some point?
I think this is the probability of being on the 40%. This is the, now once, if I am to see 6 of 8, that's going to happen 3 ways.
So the question is, F 40%, that is the posterior?
That's the posterior, yes.
Oh,
yes. Remember pi was the prior. And yeah, if it's something like that, stop me right away, because I know if you think about it, you can't move on. You okay?
Yeah.
We're at page 18. Very good. Okay, back to the original problem. It was actually necessary to set all this up. I think it would have been too complicated to try to attack this problem without giving you some familiarity with the type of things that are used. Now, in the previous trial, we had 20 subjects, there was one response. Of course, we're talking in college here. This is where this question was posed. And in many cases, 5% response rate is very good. Actually, it was good many years ago. It's getting less good now. What is the likelihood in a successive trial of 100 that will have 5 or more responses, which would be considered a success? If we see 5% response rate, well, that's good. That was many years ago. Today, I think we're doing much better in college. The solution is identically analogous to the redhead problem. But whereas that problem was contrived, this one's a bit more natural. These are real questions that people ask. Well, in this case, the population, or truth, introduce you to that truth. We don't know what the truth is. It's not known. The truth we speak of is the probability of the response. That's the truth we speak of. We don't know what it is. If we consider 1%, 2%, so forth and so on, and I don't know anything about it, I'm going to assume that each of these are equally likely. Now, this is a discrete case. I've discretized it. This also leads to continuous situations, but I won't get to that today. That's another lecture. We'll stick with this discrete case. Let's call delta P to be 1 over 100, or that's just going to be the prior probability of the actual probability being between 3 and 4%, or 5%. In other words, I can cut this up into 100 equally spaced ones. And I'm saying the probability of following each of these is 1 over 100. We've already seen data. Let's call the expression for our observation the likelihood function. Okay? The likelihood function will be the function of P, the unknown probability, treating data as a parameter. Okay, now we're treating the data as a parameter. Okay, for example, in the current cases, the likelihood function is given by the binomial. Notice that it's really a probability of P given n trials and n successive is given by this binomial distribution. Okay? So the probability of P of k, some P of k, given these conditions, is equal to the prior of P of k, multiplied by the likelihood of P of k, this likelihood, divided by all such likelihoods. In other words, now think of that oval with 100 slices in it. And that's what we're doing here. What we have is we've observed a piece of it. And we want to know what is the probability, what is our posterior probability of what's the probability of each of these, what's the probability of these probabilities, what's the probability of the percentages given that we've seen this data. And this is going to be given by a binomial n, well, it's given by this binomial for a given P of k, like 4% or 5% or whatever, divided by all such probabilities. Because the way we see 1 out of 20 is we see 1 out of 20 with 1% probability, 2%, 3%, so forth and so on. So this is a sum of 100 different things here. This is one specific one of them. And I know there's a lot of notation here, and I even have to think about it. But if you get the geometry, that's what I'm hoping you see here, the geometry of this. Questions? I know this is the hard transition here. It's the algebra. Yes. Oh, that. Okay, for example, in the current case, the likelihood function is L of P given one. Actually, it's 100 and I'm sorry, it's 20 and given one success. So the posterior probability is given by the prior distribution of the BK per given BK. The likelihood function divided by the sum of all such priors and likelihoods. And that's given by this term right here.
Ben?
Yes.
The last line, what I'm having difficulty with is, okay, we've got the binomial expression NSP sub k, delta p, and then that's divided by the sum over I of all of that.
Right.
Okay, I can think if you've got the sum of in a series, but what's the denominator? I'm not getting the distinction between.
I understand. I understand the difficulty. Okay, here's what's going on right here. We are trying to give first thing we want to do is to give a posterior probability of what is the probability of a success. Now, think of this thing as being cut up into 100. Okay? Forget the algebra. I get hung up on the algebra. Algebra you figure out later, unless you're an algebraist. I think geometry. Think of this as being cut up into 100 slices, where the ith slice is the truth that the probability of success is, say, 45%, or that's the 45th slide. The 10th slide would be the probability is 10%, so forth. And I have 100 of these. Now, given that, I have this oval, and that oval is the area in each little slice is going to be the probability of seeing 1 out of 5 successes given the 1% probability. The 100th would be the probability of seeing 5% success rate, 1 out of 20, given 100% probability of success. Well, that's 0. And these would be very small. These would, around 5%, they'd probably be a little bigger. And what you want to do is look at the stuff in the oval and say, well, what is the comparative areas to the stuff in the oval with the big oval? And that's what all that algebra was doing. But I even got lost with it. It's hard, but see the geometry of what's going on. I've got 1 success out of 20. Well, let me ask you this. If I get 1 success out of 20, do you believe the probability of success was 50%? You saw 1 success out of 20. What do you think? You think you're going to see that? You're going to have a very small, I don't think so. You're going to have a very small proportion. On the other hand, if the probability of success tends to be around 5%, you're probably going to see more of that rectangle. That's probably where it's occurred. It's that's probably about where the probability is. 6%, 7%, 5%, 4%, probably not 90%. Okay, in our particular case, the probability of seeing any particular p-value is given by a binomial. Given that p is the truth, say 45%, times, does everyone remember what delta p is? It's 1 over 100. Yeah, it was 1 over 100 because they're all equally likely. Divided by the sum of all of these things for all values of p. Remember I said, think of that big oval? The thing that we've observed is in the oval, that's what's in the denominator. All those slices. Here, we're looking at a particular slice. Now notice that that's going to go away. Now we are free to break up delta p as fine as we like. We can do it one or so forth and so on. This tends to the continuous case, but we know we can do that. finally, the posterior of P of K is given by this ugly expression here. I just restated it. And recall what B of 1 over, recall what this means. This is a combination of 1 on 20, P raised to the first power, and 1 minus Q raised to the 19th power. Yes?
Does it really matter what delta P is? I mean, it looks like it just cancels out, right? It's in the numerator.
Wait a minute, I got a question. When does that not matter?
Well, if it's equally important on both sides of the ratio, then the ratio of delta P over delta P being 1, it wouldn't matter.
It cancels. That's that's called an uninformative prior. In other words, this particular case was uninformative. I didn't know what P was. I just guessed. I said, well, I don't know what it is. They're all equally likely. And if there's any oncologists or anyone, usually what I ask the end is pick this apart. Where are my assumptions wrong, so forth and so on. It's supposed to work. All right. So this is this right here gives us an approximate equation. This is the binomial probability right here. That's the different 20s. That. Let's not move. Oh, right.
Inside the slide.
Oh. Let's just do it over here. What's the probability I can get on that thing?
That's good.
Okay. This is a graph of those posterior probabilities. If we graph these, this is what it looks like. As we see, it's probably centered about there somewhere. The 80%, the 60% aren't very likely. So this is what we use. We use these posterior probabilities to answer the original question. At least 5 out of 100. This is going to be the sum of all those cases. There's 100 things to sum here. Where P takes values 1, 2, 3, 4, 5, up to 99 is 100, of course. And it turns out to be about 72%. So that's the answer. Assuming from the result of the first trial that P was 5%, which would also be a likely thing to do, we get that the answer is 56%. That's assuming that the truth is 5%, which we also reached. If we use the Bayesian approach, we get to 72%. So last. I'm sorry? I can't do all those details, but the calculations I would have showed in there, I probably didn't say it, would have been cube problem. We would have cube binomials, reverse cubes, which I did before. When we went through this number of redheads, I wanted to say, I said, well, 6 or more. In this case, it was 5 or more. That's in each case, okay, what's probably usually 5 or more, and that's a cube. That's a reverse cube. Okay, of course, this is not the way the problem is really done, but this approach I think is instructive. At least I think the first 3/4 is instructive. After that, you kind of get hung up on the algebra. The way it is really done will be covered in the next talk, which I won't address. But at this point, what is the flaw in my thinking? In other words, I go out there and I have a trial. 1 success out of 20. And I tell the physicians, well, if you do the trial again, you're going to have, 72%? You're going to have a 72% chance of a success. Is there a flaw in my thinking? What is the flaw in my thinking? Any oncologists out there? I'm sorry?
Every condition is the same.
Well, do you think your drug's going to have a 90% probability? Do you think it's going to cure 90% of the people? That was just as likely. I assume that was just as likely as curing 10% of the people. So I think in this case the flaw really was in my assumption that I used under prior mistakes. Again, that's because of 20 years experience. You just don't get you don't have a drug that's going to cure 90% of the people. Yes.
So now, given that you wouldn't use 90 plus up there, would you narrow down the probability of your
I would probably talk to physicians, and a lot of times in the pharmaceutical, we're tasked with the objective of finding how many people do we need to have a successful trial. And what you want is you set up what are the conditions of a successful trial, and you say, well, I want that to happen 90% of the time if my assumptions are correct. So at that point, I got to ask them a question, because I'll come up with any numbers you want. But what do you think? What do you think the truth is? Because I have no idea. So yeah, one way you could do it is modify it. You say, well, I don't think it's going to be more than 50%, so you chop it off. There's also another very easy answer I can give off the top of my head. I can say, well, 50%. You do one trial, you do another trial. Which one's likely to be the better trial? The first or the second? Equally likely. So it's what is the chance I'm going to do better than I did the first? You said, but there's a flaw in that too. I actually saw data. So that modifies how I think about this. For example, if I went out and did a trial and I chose 10 subjects and 8 of them survived, and we're talking about oncology, what do you think the probability I would think of getting 80 successes out of 100 in a subsequent trial? I think we got lucky. So a lot of the answers depends on what the truth is, what someone believes the truth is, but what can we do? It's the best we can do without further information. And really, when you think about it, a trial of 20 where you have one success isn't really a lot of information.
Just want to make a comment. I
Yeah.
think in that case, it's the earlier trial, not enough to predict the success rate of the larger phase 3 trials, because once you enlarge the sample size, you get to recruit a lot of patients. Then your assumption of when you have a 20 patient trial, where you never know why those patients are enrolled. They used to be a very different.
Oh boy, you're talking about why many trials fail.
Right.
I mean, we've seen it. I've seen it all the time. We've got to get this trial done. We'll get those patients in here. Don't worry about screening them, getting them in. We've got a 90% power. Guess what happens in phase 3? You fail, and nobody goes home with negative. I've seen it happen.
Then the 1 out of 20 is not really the accurate estimate.
You've got to set up the experiment, you've got to set up the trial and say, what are my entry criteria? And when you start deviating from that, you're fooling yourself. You've got to state what you think you have. And then, of course, it doesn't go from phase 1 to phase 3. Hopefully, we've had a successful phase 2 trial, and we don't try to deviate from that too much. But yeah, in pharmaceutical, I think it's pretty standard. We want 2.5%. The FDA says 5%. You don't count that 2.5% is bad. So it's really it's 2.5% is the alpha on that, but it's really much higher because they require more than one trial. Is there any other questions? Yes.
Yeah, I have a question just regarding, I don't know what kind of disease area you have worked on before, but normally what are the response rate, for example, oncology or infectious disease?
Well, when I was doing, I don't know infectious diseases, but when I was doing oncology, this talk came about 5 or 6 years ago, and when you're in, the assumption generally made is that you're going to compare yourself with 1% success rate because you can't compare with 0. In other words, there's no cure for this. So if you see any type of response, you're going to get someone interested in developing your drug. If you see 5%, well, if I have a 5% chance of surviving as opposed to 0, I'm going to take the 5. And that's when we make slow progress.
It's depending on the current standard.
Right today, phase 3 trials are, a lot of them are failing today for this reason. They use, it's not a part of this talk, but you'll use something called overall survival. And what that means is you'll follow someone until they either, you don't know what happened to them, or they die. Well, that worked 30 years ago, but patients that come into your trial and physicians that put them on your trial aren't going to let patients die just so your trial can be a success. When they find out it's not working, they put them on something else, and they live on. And there's also a phenomenon out there, there's a placebo effect. It's real. It is absolutely real. I've seen it. I designed, we have a, no, this is what I saw in renal failure. We were seeing blinded results where we were getting 40% success rates. Oh, man, we're all going to the bank. You know, let me buy that new car. We're going to, the study failed. There was a 30% placebo effect. And that's because patients that were coming into the trial weren't screened well, and this was known. They were not screened well. Again, it said, let's get them in here quick because we want to get that $10 million, what do they call it, benchmark. If we get this done in a certain time, someone's going to give us $10 million. Well, they blew billions of dollars. What happened was, if you had subjects that entered the trial and they were well managed, then you had a very small placebo. In other words, they were taking the medication, they were doing what they told them to, you're giving this new drug, or they don't want it. But when you take them off the streets and they're not getting any medication at all, the mere fact that someone's talking to them means that they're going to have a huge placebo effect. Talking to them, treating them, making sure they're eating well. And 3/4 of the patients in the trial were of that nature. When you actually did look at those who were managed well, they had success. But that's another failure. The drug went away. It was probably a good drug, but it's not out there. It failed in phase 2.
I know this is kind of a debating from your original topic, but right now, given that personalized medicine is more and more emphasized, is that going to change the...
I can't. I don't know.
Okay.
I don't know. I have a very narrow... We become experts in a very narrow field of this vast society we live in.
That's true.
Any other questions? Thank you for your patience. I'm sorry the last part, the algebra just got too bad, but I hope I got you to see the geometry. If you understood the redhead problem, you understood the problem, the last problem. It just...
The topic is Bayesian statistics and personalized medicine. Although we know little about Bayesian inference, we know a lot about personal medicine in the Bay Area, especially around Berkeley. So I won't talk too much about what is personalized medicine, but I will focus on why we should use Bayesian inference in developing personalized medicine. So we talk about also give you an example what Bayesian algorithm can be used for biomarker discovery, okay? And to make things easier for understanding, let's take a look at this picture. I give you a hint. It is a mixture actually of two images. A 60-year-old or 20-year-old woman. Which part could you see?
20.
You see the?
60.
Anyway, this is data. And your job is to make a decision based on your inference or probability. It's a binary. Like if the probability for you to notice that older part, like this is the node, this is the month, you know, then you should think this is an older node. For those who think, oh, 80% it should be young because I noticed this part. This is small node and this the eye and you know that. So, but if I give you some prior knowledge, that is, if you saw this earlier, then what's your decision gonna make about making decision based on the data? Am I right? So that is Bayesian. Bayesian really means to make decision or inference based on the data. You also incorporate your prior experience in this reasoning procedure. If you grew up, 80% chance you see figures like that, probably you see the younger part, because that means your prior probability emphasize this one. You're more familiar with this one. And on the other hand, you may recognize this part because you live in the nursery, retirement center. Like I always visit here to see my mother.
Yeah, what's the truth? Yeah, what truth do we have?
So that is the thing. The thing is, any decision making, this for a parameter, theta here is binary, being old or young, giving the data, that's the image you saw, actually is a combination of two parts. That is, in your previous life, what is the probability for you to see either an old or younger image or figure in your life or in your neighborhood, okay? Plus, if this is the likelihood that is given an older lady, what the image should look like, or giving a younger lady, what image should look like. That is likelihood. So the combination of this give you inference. So it's like this. You come to the Bay Area from East Coast yesterday, and when you go up, you notice it's cloudy in the morning, and then you ask your roommate, should I bring umbrella with me? Yeah. And then your roommate says, no, don't worry about it. Why? Mainly because that person's prior is different from a local resident's prior. The understanding of predicting the probability of seeing rain in summer in the Bay Area is 1 or 0%. So that is exactly what you talk about. That the disease is rare. Right. That is, even though your testing or diagnostic is sensitive and specific, you still have a very small posterior probability. Okay? So that's reason. Thank you, Ben, for covering that. So I directly move to this topic. What is personalized medicine? In a biostatistician's eye, a decision, personalized medicine is based upon a statistical model, or not necessarily statistical model. Let's generalize statistical model into any model. That is a multi-layer model. You have inputs layer, you have output layer. Let's assume that the input layer consists of x1 to xn, including like your genotype, your demographic information, plus your physiological or physiological kind of measures. Then I can predict the output of using, that is the cure rate of using drug A is 80%, versus the probability of using treatment B, the cure rate is 95%. Then which drug will you use? You will use B. Right? That is the personalized medicine, because you give right medicine or treatment to the right people at the right time and location. That is personalized medicine. So personalized medicine is not a mission only done by biological researchers, but it should be a mission that requires incorporation and merge expertise from different fields, especially Bayesian or just statisticians. Okay? So personalized medicine now is really not personalized medicine. That is like you can order like some shoes online, but I bet no shoemaker at this moment only make one pair of shoes just for yourself. Alright? That's the reason actually they divide the whole population into subcategories or groups based on some kind of marker. And in the arena of biology, we call them biomarkers. And using some biomarkers at genetics level, that is SNP, for example, or at gene level, that let's see gene expression, or RNA level, or protein level, or whatever level, we can divide all the people who have hypertension into different groups, different subpopulations. And then we can try to figure out for such a drug, which subcategory really works well using this drug, just like this category. But the other category, like this one, doesn't work at all. So that is the current version of personalized medicine. So I don't call it personalized medicine. I think it should be called subpopulation medicine. Am I right?
Yes.
It's not personalized medicine. So as a Bayesian statistician, this is my dream, and this drives me for my research and entrepreneurship. Okay? So that hopefully 20 years later we can develop something, you can order your drug just for yourself, not for your peers on one of the slides. Okay? So current version of personal medicine based on DNA test, basically you shift that general population, that's a whole population of disease patients, through that procedure so that you can categorize them into more homogeneous subgroups. And then the drug under investigation may work well for these people who are happy, and it's safe and effective. But for some other people, it may be safe but not effective, or effective but not safe. And this is the worst situation. Doesn't work for them at all. So compare with evidence-based medicine. That was the current of history. Personalized medicine associated with these descriptives. It is predictive. It is preventive. It is patient-centered model of care. So that is the future. And when I graduated in 2002 from UCLA, at that time, some of my colleagues were very lucky. They started to receive genomic gene expression data analysis. And I was still use the traditional kind of observational, traditional clinical trial data to do my dissertation. But during the previous 12 years, we observed how the huge opportunity introduced by next generation sequencing. And about 2002, we know at that time you need basically $200 million to sequence a whole person. And now we only need $2,000 or less to sequence one person. And the good news is none of us have missed the train completely. Because
just mostly.
Yeah, because before 2003, the research basically was focused on to understand the structure of the genomes.
Can I ask you a question? Why has that cost come down so much? What's driving that? You said 200 million compared to 2,000. Yeah, that's an incredible.
Yeah, it's like 1% of the less than 1%.
It's trivial. Yes.
Yeah. So I'm not a bioengineer. Okay, I'm a biostatistician. I'm not the best one to answer your question.
I just wanted to make sure you was.
Just a point on this. Much of the decrease in the cost has been across all fields of instrumentation. I come from a laboratory background, and when we first got in gas, mass spec chromatography, it was like $100,000 instrument. And today you can buy instruments that are superior for like $10,000. And things have become smaller. They're integrated with computer systems. So that has driven the price down a lot. And And there are other factors, but that's at least one factor I've seen, and it's not just in genomics.
Thank you.
And all that's going to work together.
Thank you. Fortunately, in this decade, between 2011 and 2020, the focus now shift on to understand the biology of disease, okay? And then in the future, once we understand the biology of disease, we can develop intervention or therapeutic solution based on that to treat disease. But that is beyond 2020. So I think most of us are still young to see that. Okay? So that's really.
Don't get sick.
So now I'll go back to answer the question why we need a Bayesian application in personal medicine. Because of the natures of the Bayesian inference. Number one, Bayesian probability is subjective, all right? Because that is like what's the probability of it going to rain this afternoon, seeing clouds in the morning. You said 1%, because you have been here 20 years. I came from New York City, so I think 60%. Then when we talk to each other, we usually ignore our background. We only ask you what's your probability. That's the reason. Actually, in real life, all probabilities in absolute sense are conditional. Think about that. No probability is non-conditioned. When we talk about when people communicate to each other, we just ignore that condition. Okay? That's the reason we see people question, Bayesian, I don't like Bayesian because she has her probability, you have your probability. For seeing the same cloud, you guys give two different probability. That's the reason I don't like it. It's not objective. Okay? But being subjective is a blessing. That's the reason you train your truth. In China, 20 half century ago, when we sent the troops to battle, follow all the order of martial. You don't have freedom. Okay? That's the reason they can win the competition with the American troops. But American troops are gonna be different. When we send them out, we tell them, protect yourself, okay? Sometimes when you see, okay, I surrender, you should do that, okay? That's the reason. If you give people like freedom to incorporate their own intelligence or experience, their behavior gonna be based on posterior probability or conditional probability. Given the conditional probability, you make your soldiers smarter, you make your soldiers more like another friend. Otherwise, you just treat them as slaves. Okay? It's follow me.
Don't we practice Bayesian in our own?
You're right. That's a good description. All statisticians by nature are Bayesian statistics. Just they don't acknowledge. Okay? All statisticians are Bayesian statisticians. The human.
You're going to get thrown into the bay if there's any. I wouldn't do that to a bubble.
You just don't admit it. Okay? Okay. Or you try to satisfy your audience. Okay? You not to illustrate. Okay. So that's the reason. So it's a perfect match to personalized medicine because personalized medicine means it's personalized. So Bayesian is subjective, okay, personalized. So that's literally interesting, okay. But this is important. These two reasons I think about it. Small sample size for rare disease, and according to at the molecular level, you don't really think one person will have exactly the same cancer as another person. You think about that. So the sample size will convert to 1. in the future? Because every disease is going to be different from another. What's your sample size going to be? N will converge to 1. So N going to be smaller and smaller. Then you cannot, based on inference, assuming large samples here. That's basically one reason. Second reason, as you been illustrated, using Bayesian, you can be easy to be adaptive. That is adaptive clinical trial or design or decision making. That means if I have currently observed 1 out of 10 people with response in the clinical trial, should I take a look at the data and pick my data and use that to predict in the future if we collect 100 more people, whether we can see more than 10 response? That is exactly adaptive design, which means based on my today's data, I predict the future. If that chance is so small, then I stop early. I won't waste my resource. Okay? And similarly, if I observe the 9 out of 10 success so far, what will be the probability of seeing 60 or more response if I continue to recruit 100 more people? If that probability is over 90%, then we should not waste our resource to move on. We open champion and enjoy our celebrities, that right away. So that is the reasons why Bayesian. But Bayesian, as we will later see, have other advantages. And then now I gradually to move to the top to a case study, that is the biomarker discovery. And what is a biomarker? A biomarker, earlier we said it could be at different molecular levels, but of course it can be defined by your purpose. Okay, it could be there at least 8 types of biomarkers based on function. Now, I'm going to give 3 examples. Prognostic biomarker. That is, if measure a person's like a gene expression, I can predict whether that person will have a higher risk getting certain cancer. That is, that gene or set of genes will be called prognostic biomarkers for predicting that person's future. This is for predictive medicine purpose and for preventive purpose. And second, once we know this person have a higher risk and later that person really have disease, you want to give them a drug, chemotherapy or radiology therapy, which one? Okay, then you need to do some kind of other types of biomarker test. Using other genes, for example, you can tell me which person should use chemotherapy, which person is not good for chemotherapy. That is called predictive biomarker. That is to predict the efficacy of a certain treatment. And similarly, we can see other things like a pharmacodynamic biomarker. That is, using chemotherapy to this person, but what is the dosage level you should give? And then you can use other biomarker, maybe RNA level, to tell me, oh, this person should give this high dose, but another person with this RNA profile, you should give them lower dosage. So I only give 3 examples, but there are much more.
I just wanted to clarify my understanding here. So the predictive test and the pharmacodynamic test, they're both referring to when patients are already discovered that they have the disease or after certain treatments, right?
You're right. This is, I know that is a patient, and I want to tell the patient which drug or therapy she or he should use. This is, I know he should use this drug, but what's the dosage level I should use? So I should skip this one. That is in the current FDA guideline require new drug development should be like a parallel kind of procedure. Left, you are looking for that therapeutical reagents or kind of chemical drug. The right side is you are looking for a biomarker associated with this drug, so that in the future, once this drug is verified its efficacy, you need to tell the audience which population, based on certain kind of blood testing, should use this drug, and others should not use. And in clinical trials, we have a traditional, simple, two-arm random trial design. And we have Bayesian adaptive design. Bayesian adaptive design basically means you can, as the situation change or as our understanding about the disease progresses, we should modify or change our protocol. Otherwise, if later, 1 year later, you know there is a new drug or some other people said this doesn't work, will you still continue your protocol as a 5-year plan? Probably not. So you have to revise. To revise, we need to use Bayesian, we need to use adaptive design. And one idea is to adaptively assign patients. For example, if after half a year we notice the cure rate is 60% in arm 1 and 30% in arm 2, then in the future we should randomize 2 into arm 1 and 1 into arm 2, because the first arm have twice high efficacy compared with the second.
And what does that, when you explain, why would you do that?
Because you want to benefit the study participants. You know, arm A have a higher efficacy so far, then you want to throw more people into that arm, which has more benefit.
What does arm A mean? What does the arm refer to?
The arm A refers to clinical trial. You have arm A may be a drug, arm B may be a placebo,
Okay.
for example. If later you realize the arm A, 60% placebo, 30%, then you can change. You should change your assigned ratio. In the previous protocol, maybe you pre-assigned like a 1-1 randomization, but now you changed it to 2-1 randomization. Okay, but that ratio dynamically to be adjusted, because after 1 year you found that the first group has 80% cure rate, response rate, and the placebo now become 20%. So you should change the ratio to 4-1 instead of 2-1. You see, you continuously adjusting your ratio.
Is that to encourage subjects to enroll into the study? Because I see that's where that would be the benefit. If I'm coming into a study and I get 4/5 a chance of getting something I think works, as opposed to 50-50 chance, I might be more willing to partake in the study. That's where I see the biggest benefit for that.
Or are there other benefits?
Yeah, there are other
to-
benefits.
Yeah, there are other benefits.
Yeah, but what
Yeah.
about the benefit of coming to, in other words, the purpose of the clinical trial is to get the drug approved if it works. And if you're splitting it up like that, you have to have a pretty large data set in order to convince someone that you have a successful trial. But yeah, that's done quite often, that they'll say, well, if you're going to go in the trial, you've got a more chance of getting active drug than non-active.
Yeah, because any experiment in the future, you should balance ethnicity, benefit, and efficacy, and proficiency. You should balance all, consider all those factors into that. All right. So these adaptive assignment people mainly reflect our, efficacy, our effort to improve people's health. Okay, that is one concern. But of course, we have other things like interim analysis. We have to do interim analysis occasionally to summarize the data so that you predict the future. That is what we call using predictive probability. That is the predictive probability. Seeing 1 out of 8, then you want to predict 6 out of 50. Okay, in the future. That is that. Because if your probability, your predictive probability is small or very big, you can pre-terminate your study. That will save you money and save you sample size. Okay? So that's the reason this interim analysis, economical point of view, will require on average smaller sample size and short study period. Okay? But this is to save time and money. But there are many, many concerns in here or factors, and I don't want to talk about that. Okay? There is a very good book called Bayesian Adaptive Method for Clinical Trial, and that is I spent the whole semester to introduce that book. Okay.
So this is, you're saying treat a clinical trial as a multi-arm bandit problem? Is that like the framework? And then use a Bayesian approach to solving a multi-arm bandit problem?
Even traditional randomized trial, randomized control trial may use multiple arms. They all use multiple arms.
Yeah.
The traditional is you cannot pick or take a look at your data until the end of the study. Okay? So you fixed, I will recruit 100 people, 50 randomly into arm A, 50 randomly into arm B. That's, you can only analyze data after you finish collecting these 100 people's data. But a Bayesian analysis allow you to look at your data 3 times in the middle. Okay? The first time I look at the middle when I have 30 people. And then the second time I look at data when I have 60 people. And then the third time, maybe at the second time you can predetermine it has efficacy or it is a failure. Okay? So that is adaptive.
Does this have to do with FDA regulation?
Yes, you need to communicate it with the FDA, and FDA need to give you approval to use this study design. And now, for medical or diagnostic kind of assay development, FDA is very open. Almost half, more than half, use adaptive design. For human disease, like for cancer, phase 1 trial, phase 2 trial now have almost 30% to 40% using adaptive. Okay, but for phase 3 trial, no, usually not, because that is a confirmatory kind of study, maybe less than 10% adopt with adaptive design. Okay, so being adaptive design doesn't mean you have to use it across all the 3 phases of clinical trial.
It also depends on the kind of adaptation you propose. I work in Alzheimer's disease phase 3 trials, and it's possible to adapt on things like the variability of the measure in comparison to your previous assumptions about the variability, but not to adapt on the kinds of things you're describing. Also, I think adaptation in general only works when the ability to detect a response is short compared to the treatment period necessary to really confirm the response. So in my beloved disease, we have 1,000 biomarkers, but none of them are validated to predict clinical response. And the treatment period for Alzheimer's disease is 2 to 3 years long. So you can't. We have not found a way yet to introduce biomarker adaptations, because we don't know the linkage between the biomarker and the clinical response. It's great. You can learn all kinds of things, but you don't know how to use it yet.
You're right. That is also another challenge.
I was hoping you would.
During 2 years study span of clinical trial, half a year later, maybe Stanford University publish a new paper suggesting I found a biomarker now, and half a year later, Yale published another paper, giving another set of biomarker which is better. Then you have to constantly face the changing of the world outside your lab. Will that influence your work or not? So that is another challenge. That is, but how to do biomarker-based personalized medicine development? You need to think about new type of design. Like you have to consider not only treatment now, you also have to randomize your people into different marker groups based on biomarkers. And sometimes at the beginning of the year, gene A is a biomarker, but after half a year, gene A and C together is a better biomarker. You have all to change. Okay, that's a reason to be adaptive. Gonna be unavoidable in the future, but how the Bayesian clinical trial will be? Bayesian clinical trial actually is based on posterior interval or credible interval. That is, if, let's use two-arm study, for example. If my estimate, the parameter is like a difference in response rate between standard and the control, between the drug and the control arms. And then you can, using some Bayesian algorithm, to derive the posterior confidence interval of that difference. That difference reflects the efficacy. If that difference, like within this 95% interval here, then you basically you see this is the equivalence kind of study. This new drug is equal to the standard comparison group, okay, in terms of efficacy, because the difference is around 0, and this is delta L and delta U give you a width, a bandwidth, not bandwidth, an interval or zone that is called non-differential zone. For example, delta L is -2%, delta U is +2%, which means if the response rate difference between the two groups is between negative and +2%, then basically no difference. Then if your confidence interval, not confidence interval, posterior interval, falls into that non-differential zone, this is equivalence test. Otherwise, if that confidence, that credible interval, posterior interval, falls on the right of this threshold, then you see you will accept the treatment because treatment has more than 2% difference. Otherwise, here you accept the control. Or other places here, for example here, if it's include the upper threshold, then you reject control, but you don't accept treatment. So you have no decision if this interval is so wide. 1, 2, 3, 4, 5, 6. You can make 6 types of decisions based on posterior interval. Okay? And prior, when you have prior and you don't have prior, you may have different strategy. When you don't have prior, for example, you may assume non-informative prior, that is, the difference is around 0. It's a normal distribution around 0. Or you may use another prior, you think the center is around here. That is favorable to you. Or FDA may require you need a prior center as a negative place. That is favors FDA. So you need to play with FDA to negotiate with them which prior you should use. Okay. And now I move to this second part. From here, I talk about what my company is doing. 5 years ago, I read a book, and I saw this figure, and that triggers my career to develop software for solution. Here, assuming you are a physician, you have a 60-year-old customer, a woman, came to your clinic. You ask your nurse to measure her systolic blood pressures to determine whether that lady is hypertensive. That is your decision making. That decision making usually based on your confidence interval, because your measure your blood pressure meter, as any other devices, has some margin of errors. So let's assume the margin of errors is like a 5 mmHg. Then you will see, oh, her mean value is 130. But because the device have standard error, you need to plus and minus twice of that to get a 95% interval. And that 95% confidence interval is usually what you see on your check-up results, like physical examination. For all kind of blood testing kind of measures, you were giving an interval. That is a 95% interval. And if that 95% interval excludes 140, which is like a cutoff, if over than 140, then usually that person is labeled as hypertensive. But the physician feel reluctant when that 95% interval contains 140 in that if that interval is between 120 and 140, and 140 is on the right edge, at this moment you may have good confidence to claim that lady hypertensive. Okay, but still this is on the edge, the 140. What usually you do? Fortunately, all physicians are Bayesian. Why? Because they always ask you a question. Are you a smoker? Did you smoke before? Why they ask you that question? Mainly because if the lady tells you she never smokes, then you will know that lady is a member of a population of non-smoker population. And from surveys or epidemiological study, you know the distribution of all ladies without tobacco use, their distribution around 120. What does that mean? That means the physician will intuitively calculate a posterior probability, a distribution for systolic blood lady, which will be a weighted average of 130 and 120, and probably around 128. Maybe she or the physician doesn't know exactly quantity, but the physician is very happy. You have no blood pressure at all. Okay? Which basically triggers me this thing. That is, I worked at school public health. And school public health, we don't have much money at profit compared to medical center, hospitals. But we all know now, physicians' decision making, they make money based on this and this and this. Did they pay loyalty to you? Epidemiologists who created this database? No, they never pay you. But does this contribute value to healthcare decision making? Absolutely. Okay, so that's the reason. If I can develop a software that will do the calculation explicitly to help physicians making more clear decisions, does that have value? I think it has value, and this is a generic situation across all kind of diagnostic for disease, check the diagnosis, even for treatment. This is another example. But 6 years ago, I worked 8 years ago at UCLA with another biostatistician who developed this idea. That is, as a physician making decision in local clinic, he or she makes decision based on two things: local evidence, that is either she or her or his own data, that is the personal experience, that this drug works for this 60-year-old lady, hypertensive lady. And that data, if the physician works in a big organization like Kaiser, maybe she's lucky or he is lucky to have evidence from many clinics, hospital 1, hospital N. Then they pull all those data into your system. And when I go into that data system, I can do simple logistic regression, giving the person's X, X1 to Xn. Then what's the probability of a cure rate for this drug A versus drug B? I can get that. Okay? And Kaiser is doing that. But usually the decision making is not only based on this local evidence, because of two reasons. Number one, there wasn't yet infrastructure taking advantage of the local EMR system to make decisions like this. Second, those physicians, do we have physicians here? Sorry, I should lower my voice. Okay. Because physicians' number one concern is not to make a right decision, but to avoid make bad decisions so that they are sued. I have to see that. That's the reason. Even though I give you this system, you won't use it because you will just follow the guideline either from WHO or whatever. That way, even though that doesn't work, it's not my mistake. Okay, I follow the guideline. Okay, but we all have this mission. That is, if we build up this global knowledge base that curate available clinical trial database or literature, all from epidemiologic studies, we combine that into knowledge and tell you that according to this domain, drug A successfully treat 80% of these people like this client. Drug B only treat successfully 60%. Will you consider that? Yeah, you will follow that. Plus, this local person, even though that drug have evidence from all over the country or even internationally, you are not treating that population. You are treating your patients locally in your neighborhood. And that people may be unique compared to other people, 60-year-old ladies around other places. That's the reason a right decision should be a combination of my local, my personal experience. I know more than anybody else about my patients in Berkeley. But I have also have to combine the knowledge from the global, because my sample size here is low, maybe only 500. These were based on 500,000 people. So that's really, even at the nationwide level, we need to build up something called evidence-based empirical Bayesian statistical engine to combine those things together. Okay, so that's the two figures reflect my motivation in developing a company or software. So what our mission is, we are dedicated to combine biostatistical expertise with information technology to foster the emergence of personalized medicine. And all those things you think about that, these are personalized medicine in the real sense. Okay? Because I treat different people differentially. That's personalized medicine. So what we developed is we are the first group probably in this country receiving the funding from NIH on develop a mobile phone-based system with data collection and a patient monitoring system. That was in 2008. So we started from there, our story. So we developed mobile app running on iPhone and now Android to collect medication behavior, physiological and environmental kind of data. Because our philosophy is the disease is caused by environmental things, including behavior. So we need to have those. And we have these variable computation, like all the sensors around wirelessly attached to your body to contribute the data. Once we have that, we pull that here into our cloud. That's the system we are building. And also, currently we have these following products. Number one, we have genetics 365. We think gene and molecule, provide biological sense to influence your health. So if we could figure out the available biomarkers in predicting all kinds of disease, and if we put that into your arm, into your hand, via an iPhone or iPad, that could help personal health decision making. So that's the first product. We just developed an interface running on the iOS devices to access the SNP database. Okay, so all available published data, and now organized by NIH, not us. We don't have enough time to collect all those data, but we take advantage of available data online and put that to be intuitively displayed over your hands. That is called genetics 365. Plus, we call this EMA 365, ecological momentary assessment, which is an iOS app that together with medical devices and instruments or event, we call that either questionnaire or event trackers, you can track your behavior. That way, we pull those things together. We think that is the cornerstone for personalized medicine, because all the disease gonna be based on genetics and behavior.
So I've always, so I have Kaiser, and they give me a solution for whatever my problem is, and then they don't follow up, to see if that it's the right diagnosis and what did I do, what are the confounding other things that I didn't. So just thinking, it'd be great. Like, do you collect or do you plan to collect after,
Yeah,
after
we
treatment?
do that. Yeah. That is what we are doing now. We call it ePro, electronic patient reported outcomes.
Oh, yeah.
Okay? So after you receive the treatment, you need to have that instrumental application at your hand to report your behavior and treatment results. That way, your doctor will know how good this treatment or therapy applied to you. Okay, and that is also for the purpose of comparison effectiveness. And I need to move quickly for the second part. That is called model selection. That is another project funded by NIH in developing a biomarker selection procedure. And model selection is a fundamental task. Any model selection is based on two principles: goodness of fit and parsimony. A simpler model is preferred if the two models are equally well interpreting the data. Okay? And the model, the model should fit the data well or explain the data well. That's the two parts. So all models are wrong, but some are useful. That is our philosophy.
Was
because
that the Fisher information in there?
Sorry?
Was that Fisher information in there?
This is the Fisher information. This is number of parameters in the model.
Why is a simple model better?
That is a good question, because that is all acceptable. That is a default assumption by most modern scientists conducting research. Why? Simple. Think about the Big Bang theory. Why people think about it starts from a point, singularity point? Because we observed all the objects in the universe, they are moving apart from each other, which means the universe is expanding. If you think the universe currently you observe is expanding, what is yesterday? Yesterday should be smaller than today. And then you use that assumption, how about a million years ago? Then you shrink, then you should start from point. That's the reason people think about that. And thought this is scientific statement, because it is really based on simple assumption that it goes this way. But how about actually it starts from here, then goes small, and goes up, goes small. Then how can you reject that assumption? That's still possible. But if you think about that model is more complex, it requires more number of parameters to interpret or describe. That's the reason we prefer to use a simpler model to interpret observations. Doesn't mean that model is wrong, or doesn't mean that model is right. So in scientific field, we should not tell people this is wrong or this is true. We can only tell people my theory can interpret the data so far. That's all you can see. All right? So remember that. That's the reason we see all models are wrong, but some are useful.
You mean all theories?
All theories. All theories. All scientific theories. Because the most famous folk in the 20th century actually talking about falsifiable. Well, what's a noun for that? Falsifiability?
Falsibility.
A falsibility.
Falsifiability.
Falsifiability.
That's it.
Yeah. Falsifiability. That is the definition of science.
That's right.
Yeah. Because if I tell you some theory, you can reject that theory. That is a scientific statement. Otherwise, it's not. If I tell you God creates the whole universe, this is not science. This is a belief. This is faith.
On simplicity versus complex models, many complex models can never be falsified. So they fall outside of the domain of science. Like, it's that simple.
It's the principle of Occam's razor.
Yes, yeah, absolutely. I was trying to think of that.
There's another way to relate. You want it's simple, but not too simple.
Yes.
You want it to be just complex enough to explain everything.
Right.
But it's the same as overfitting and underfitting.
Right.
You want to be right in the middle.
Yeah, you're right. You're right.
I was trying to think of that, man.
Yeah. Yeah. That's wonderful idea. know.
That's about
But,
1,000 years old, isn't it? It's very old. No, it's very
it's
old.
like Newton. Think about the physics mechanism, it's like that. And many years people couldn't reject it. But Einstein later, the relativity could reject it. You see? That is science. Science means I believe it today, and my offspring have a hope to reject it or refine it. If I tell you a theory, nobody will refine it or improve it. That's not science. That is belief, or that is faith.
Michelson and Morley, they showed it was wrong. Einstein came along and said, well, let's try this one out. But it was Michelson and Morley that said, hey, this isn't true.
You're right. Many situations, because the theory explains many phenomena that people start to think this is truth. Okay? And they forgot it's a theory.
So was Newton's theory simpler than Einstein's though?
Yes.
Yeah.
Well,
But,
Newton's theory still applies.
Yes.
It's
It's useful.
mass times acceleration.
Yes.
But
It
when
depends
you
on your
start to
priors.
move at the speed of light, you find that your predictions are way off. And the theory of relativity, the model of relativity, if you like, gives us a much better prediction of where things are going to be. Okay?
I'm
So
not a
it's the
physicist.
ability to predict. And if you can keep things simple, then you can make predictions. It's also cheaper.
yeah, you're right. So that's the reason not everyone really understand Einstein's theory. We all just use Newton's theory in our general life, all right? Yeah, but I'm not a physicist. I know more about traditional Chinese medicine. I use these. The idea is this: in traditional Chinese medicine, it's based on many models. I only show one model that is called five phases model. Basically, 3,000 years ago, people did not have modern technology or engineer technology to really use a microscope to understand what the universe is made of. So they thought, oh, how about I invent 5 phases: water, wood, fire, earth, metal. And I think all the universe, everything in this universe was made basically out of these 5 basic fundamental elements. So first, it's simpler, okay, compared to 108 elements now, the chemical, you know. Yeah.
It seems true. Yeah.
You're right. 3,000 years ago, okay? Think about 3,000 years ago. And then, why they introduced 5, not 6, not 4? This is the question. So a simpler model can't interpret many things because it's too simple. We need a model that is complex enough, but cannot be too complex. So we need a right level, 5. Why? Because I invented these 5 elements because I want to use that 5 elements to describe all kind of relationships in this universe. What are the relationships? First, generating interaction. Second, overcoming interaction. Basically, I think our relationship, either we are enemy or friends. Okay? That's simple. Then you can see, if I use a 5-node graph, I can see water can generate wood. Water can be generated by metal. So you see, it's a pair. A friend, he make. A friend making him. Generating relationship. Overcoming relationship, I use the rest 2 to show you water can kill fire and earth can kill water. You see? Overcoming relationship. And I need 1 on the top, 1 on the lower extreme. You see? I know to describe all kind of relationship in a simplistic model. If I remove 1, then you have 1 with 3 other. Then it's not symmetric. No? So you need two enemies, one kill you and one you kill. You need two friends, one making you, one you make. So being symmetric is a principle. Being beautiful is a principle. And adopting that principle into designing the Apple device, that's what Steve Jobs said. There is no wrong or right in science. So if I develop this model, that model is smaller enough but good enough to describe this relationship. And then I try to align or mapping my organs, internal organs in my body, into one of them. For example, liver belongs to wood, heart is a kind of fire. You see, that's what they try to do. Once I have the model, then I need to use that model to interpret human body. And then in order to treat a heart problem, that is fire. If the heart is hyperactive, you want to quiet it down. You can do that in many different ways because you can't direct touch that heart, but you can do this. This is fire. To pull down fire, I can enhance water. And where is water? Water is kidney. I can enhance my kidney function of enhancement. Okay, make my kidney more active, then it will quiet down the heart. So in Chinese, medicine deal with health. The definition of health is simple, being balanced. Okay, so think about that. You and environment, internally, your heart and kidney, everything needed to be balanced. It's not for you to just cut something out and treat the symptom. You need to adopt that whole kind of holism. Okay? So Chinese medicine or doctors do not need to resort modern Western technology to prove it's wrong or true for Chinese medicine because it's based on a theory. It's no true or wrong. It's useful or not. And 3,000 years later, I still go to see Chinese doctors. So it's still useful. Okay? That's all. So a Bayesian strategy for model selection is for any generalized linear model, you need like X, let's say I is, ignore I. J from 1 to P, you have P predictor, X1 to XP. And for each predictor, you have a regression coefficient. And that regression coefficient is a function of gamma. And what gamma is? Gamma equal to 1 if the corresponding predictor is selected. Gamma equal to 0 if xj is excluded. Okay? The simple list function of beta gamma is when gamma j equal to 0, beta equal to 0, then you just remove that xj from your equation. Okay? Otherwise, beta is non-zero, so xj is included. So your model selection now becomes a question of gamma j equal to 1 or equal to 0. That's the definition of gamma j. So here, the task is, let's use this, simple. If I have x1, x2, x3, 3 genes, I want to know which gene predict an outcome variable, for example, blood pressure. Then I have to collect some data. After I analyze that data set, I can tell you this gamma is a vector, it's a model. So each model will be indicated by gamma. For example, gamma 1, gamma 2, gamma 3, you have 3, P equal to 3. So gamma 1 equal to 0, gamma 2 equal to 0, gamma 3 equal to 0, which means it's a null model. No predictor is selected. Otherwise, if B of equal to 1, like this one, all x are selected. So then this is the full model. That full model, the posterior probability is 0%. And the first model is the best model that you select x1 and x2, that gamma 1 equal to 1, gamma 2 equal to 1, gamma 3 equal to 0. The posterior probability is 40%. So on and on. From here, you look at this model. This is called Bayesian model selection, based on the posterior probability of each model being selected using posterior probability. And from here, you will notice one thing. That is, in many situations, if I only collect 100 people's data, the model suggests, the data suggests this top model, x1, x2 are the predictors. But somebody argues the second model, which select x2 and x3, have 30% support by the data. Do you really think the first model is the right model? The second model is the wrong model? This is the reason Bayesian statisticians tend to believe all models are wrong, some are useful. I don't know which is right. But if I can cut somewhere, if I use these 1, 2, 3, 4, 5, 6 models and use these as weights to do weighted prediction in the future, not going to be better. Then I only use one of them, ignoring the rest. This is called Bayesian model average. So basically, this is the model selection. How about this? x1, x2, x3, you have this column, 62%. So this is called the probability of gamma 1 equal to 1, which means x1 being selected. What's the probability? That is the marginal posterior probability. You just sum. That is the probability of x1 being selected or included into any models. And you see 1, 3, 7, and 8. These 4 models including x1 into it. And you sum their probability, 0 plus 2 plus 20 plus 40, you get 62%. Similarly, you have 75% for gamma 2 equal to 1, and 35% for gamma 3 equal to 1. Giving your data set, this is posterior marginal probability. Then giving this, I call these probabilities Bayesian variable selection probability. And that is used for me to tell you, according to this data, which gene is more important than the rest. So X2 is more important than the rest if you select only one. If you select 2 genes, I tell you X2 and X1. Okay? So that is all the thing. For any problem solution, you need to base on either models or summarizing the models. And I summarize the model to give you variable selection probability. The problem is in conducting biomarker discovery from gene expression data, you have more than 20,000 genes. So it's gamma 1 to gamma 25,000. Okay? And false positive discoveries, we compare samples gene by gene. That was done by traditional solution. That is, for each gene, I compare cases and controls, the patients and healthy comparables. I end up with multiple comparison problem. By chance, there are going to be some genes turned to be differentially expressed between patients and healthy people. So finally, if we go online, now there are hundreds of databases. Jointly tell you the relationship between genes. That is the systems biology. That tells you all root camp networking. Okay, now when I know in my data set, I have 25,000 genes and 100 patients, 100 case controls. If I do comparison of these genes univariate, one after the other, you're gonna have lots of troubles. the gene connectivity is ignored. First. Second, for example, if one gene is always like 100% correlated with the second gene, do you think you treat them as two independent comparisons? Probably not. Actually, you only do one. But how about the first gene and second gene is 60% correlated? How you incorporate that 60% into your structure? You see, there are gonna be lots of problems with that. So what we did?
Yes, the G was studied like when they were explore the originally it was very simple univariate approach, but then they sent multivariate, then multidimensional. Then there's so many pathways, but these days I heard like the G was not even good enough when they were incorporated multidimensional because the pathways like think about G like what we discover like for popular gene that's SMP is like how many million? Anyone can make
Yes, 7 million.
7 million.
Sometimes
Yeah. So
7
the
million.
pathway is huge. How do you analyze the pathway?
So what we do is this is a good question. Let's only focus on genes. Later, I can talk with you GWAS later, okay?
Oh.
We don't have time.
Oh.
Genes belong to pathways, okay? Which means this is the first pathway. You have many genes. There are some networking relationship between these genes, and we will incorporate that into our structure for analysis. So for this gene regulates this gene also regulates this gene relate to this, you see, and these genes may be independent with this. I need to incorporate that into my analysis. Okay? Number one. Number two, I believe genes are like individual people. The civilization is not due to one single or individuals independently. It contributed by a group of people. For example, this is the Berkeley community, this is the Davis community, this is the Los Angeles UCLA communities. They all contributed to this clinical outcomes as pathways. And then our job is we want to tell you which pathway is more selective. And then within each pathway, which genes are more selective, as shown by this picture. This pathway and this pathway contribute to this clinical outcome. One. But this pathway doesn't. This pathway contributes to another clinical outcome. Okay? And within this pathway, you see these 4 genes are more contributive to these 3 genes. So I need to give you quantified results about that. That is, I introduced gamma J, that as I did define, equal to 1 if gene J is selected, otherwise it's equal to 0. And cassette K, J here is a subscript from 1 index from 1 to 25,000. K indicates the K pathway ranging from 1 to big K, that you have big K pathways. So cassette K equal to 1 if pathway K is selected, otherwise it's 0. So, and then somehow this is missing, but we are not working as statisticians in my lab now, so we skip it.
So
Okay.
this method is useful for both the prognostics as well as the diagnostics, right?
Depends on your data. Okay, if your data is like comparing 100 patients with 100 healthy controls, then this is like a diagnostic marker, prognostic marker. Or if you have comparing 100 people receiving 100 patients receiving chemotherapy with 100 patients receiving radiotherapy, then this is like a selective, drug selective biomarker. Okay, depends on your data, but all work the same way here. So all I need to tell you, genes gamma 1 to gamma p, solid means selected, hollow means excluded. And pathway Ksy1 to Ksk tell you whether each pathway is selected into predicting the outcome or not. Okay? And this is the key point. That is, we need to pre-specify the prior distributions for Ksy and gamma. For Ksy, we think simple. It's just a product of K, big K. Let's assume K equal to 20. We have 20 pathways. Each pathway follows some kind of Bernoulli distribution. Okay? And then they are independent. So you have a product for 1 to 20 Bernoulli distribution. This is my prior. And what is phi? Phi 1 to phi chi. If I have some information from literature, I can use that. Otherwise, I use flat prior, treat them each like a 1% or 5%, depends. Okay, we can talk about that later. But this is the key. Gamma is a vector. Gamma 1 to gamma p. P could be 2,000, not 25,000, because we do some preliminary screening. We threw out those genes with bad quality. We only keep like 2,000 genes. So P, gamma 1 to gamma p. Using this small network or pathway for illustration, each dot is like a gamma, is a gene. And this is gamma 1, this is gamma 2, gamma 3. Gamma 1 equal to 1 means this gene is selected. Otherwise, gamma 1 equal to 0 is 0, indicating this gene is excluded, similar to other things. You see, different combination. It's like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, like switches. You switch, the bulb is on. You turn it off, it's dark. And the joint distribution of this status determines which genes are selected, which genes are excluded. Okay? So this vector is a random variable. And that random variable has a joint distribution proportional to this exponential. See, this is called Markov random field. Markov random field. When this is like a binary, this is called the Ising model, which means this. If, for example, let's using 1 for illustration. This joint model can be decomposed into conditional model, product conditional model. And this gene, gamma 3, equal to 1 or 0, conditioned on your rest. Markov chain or Markov random field tells you this. It only influenced by the neighbors. Who is the neighbor of this gene? This gene is the neighbor because there is a link to him. And these genes, 1, 2, 3, 4, 5, 6. Those other 6 genes, including this one, this one, are also your neighbors. Those genes are regulated by these genes. And this gene regulates the current gene. If all the other 6 neighbors, their status shows gamma equal to 0, which means they are all exclusive. How do you predict the current gene being exclusive? Very hard. Otherwise, if all the rest, they all are selected, then how do you think the current genes should also be highly selected? So that's the idea of this equation. So that equation reflects our philosophy that the selection of each gene should not be dependent from the rest. It is related to the neighbor genes on or off status. That is what the incorporation of the knowing network with each pathway.
It just seems like with new knowledge every day, how do you
That's a good question. All the papers, they said published 2012, okay? Then you can do the same thing 2014 to give update conclusion. When we analyze that, we only analyze that to draw from KIGG, KIGG, for example. We download the network today, and we need to tell the audience that. But 6 months later, when we do the same thing, we will change it. Okay? So we only show you a simulation study when we constructed 19 pathways with 315 genes. And then we have 50 samples, 25 cases, 25 controls. And we want to show you the true model is this model. That true model is this model. The fourth pathway, 6, 11, 12, and 15 are true or causal pathways because those genes, only genes from those pathways were selected artificially in predicting the outcome. Okay? And in the fourth pathway, the causal genes are 56 and 57. These two genes are causal genes, are true genes, artificially selected. And then this is like the regression coefficient. That is reflect your effort size, effect size. And these color vertical line indicating the probability of each gene. You have 0, 1 to 315 here. Each line here indicating that probability of the corresponding gene being selected into predicting the outcome. And as you can see, those red colored lines associate with these true causal genes. And their probability of being selected or the corresponding indicator gamma j equal to 1 is high compared to others. So it verifies this method. Second, this tells you pathway 1 to pathway 20, the posterior probability of each pathway, that is the cassette 1 to cassette 20, being equal to 1, or the corresponding pathway being selected. These are the probability, the posterior. And we see those 5 pathways being correctly identified. Another beautiful thing for this is this. In this pathway, that is pathway 4, there are 2 causal genes, 56 and 57, were true predictors. But many other genes from that pathway were also incorrectly selected. Because you see, their posterior probability being selected are equally with these true predictors. Why? Because we artificially set the pathway, the correlation between these genes are very high. When you simulate the data, you have a higher chance to set all kind of links and edges between the nodes in that pathway. So that means your lab, everyone communicated to each other on daily basis. When you finally win the Nobel, who should go get the title? Okay, so probably these 2 are the leader, but all other people equally could have a qualification to share. So this is the driver-passenger problem. So you can find the driver, all of the passengers who always stay in the same car with the driver. So this was not something bad, it's something good, because if I'm going to select a marker, it doesn't matter whether that's a true marker or wrong marker. It's just for practical purposes in many situations. But of course, if I can develop a genetic therapy to treat the patient, maybe a different story, because that requires causality. That need to find the real cause. But if just for drug developer, we don't need it. So that's all we develop for this algorithm. And this is something where you put the line, to put the level, higher that level, you think those are significant result you select. So these, everyone is familiar based on cross-validation. Okay? So I stop here because I prepare more than we need. Sorry. So I stop here. If you want to know more about my company, Bayessoft, we call us Bayessoft because we are Bayesian, developing software. And this is the beautiful logo reflecting our IT concept. Okay. Thank you very much.